Welcome, everybody, to the second of our combined TWed and paper discussion groups for this term. Just a logistical note, as I said before we started, there are other opportunities this term before the end of the term to do either paper discussions or TWed topics of your choice. Please contact me, let me know. We're very excited that we're finally going to learn all about DeepSeek, all of the things we've been hearing for the past couple of months. It's all going to be exposed by Danielle. So thank you very much for agreeing to do the talk today, and we really appreciate it. And let's welcome Danielle. Great.
As John mentioned, we're going to be talking about DeepSeek, specifically DeepSeek-R1 and the reinforcement learning that was done to incentivize reasoning capabilities, specifically in large language models. I've listed the authors out here that were listed in the appendix as core contributors, but it is worth noting there are over 100 authors listed on this paper, including the DeepSeek AI itself. So a lot of people worked clearly really hard on this, and if you get the chance, I do recommend checking out the paper itself. So to start out with, the general gist of this paper is that large-scale reinforcement learning, particularly that without supervised fine-tuning as we're used to, produced some pretty powerful reasoning capabilities in a large language model. And the DeepSeek-R1 model is comparable to OpenAI's latest model, O1-1217, on a good number of reasoning tasks. Additionally, distilling the reasoning from these more powerful models into much smaller models as a number of parameters greatly improves their performance. That as well later on. I'm going to go through a little bit of background, then talk about their model R10, and then their R1 model, which is the big one that we're hearing about all the time, then go into some of those distillation experiments I just mentioned, and wrap up with a bit of a discussion on the results and whatnot. So starting with the background. They aren't using reinforcement learning to train a large language model from scratch. They are using a base model. For this paper, the base model is going to be DeepSeek v3 base. It's a transformer-based model. It is using a multi-head latent attention mechanism that uses caching during inference. In my opinion, more interesting part about this base model is that instead of a traditional feed-forward network, they are using a mixture of experts model there. Now, reinforcement learning has been thrown around a lot. In case you're unfamiliar, the goal of reinforcement learning is to learn some optimal policy to maximize a reward. Generally, this takes place with the model interacting in some environment. In this case, that is prompts that it is being trained on and producing responses to. The policy can be thought of the decision-making process, or what process is happening behind the scenes to produce specific outputs. And the reward function in this case is how well each response does. Usually this is a scoring function, although as we'll see, not necessarily. Now, group relative policy optimization is a type of reinforcement learning. Specifically, it is an improvement on the reward function. So traditionally, reinforcement requires a pretty large, sometimes costly critic model to say, hey, you've given me this response, and I think it's worth 5 points or 10 points or 0.3, whatever metric you're working with there. But of course, these critic models, as I said, are large or costly or themselves may be biased. So instead of using such a model, GRPO instead compares and ranks responses within a batch. It will ask the same prompt a bunch of times, look at all of the responses, and say, okay, I think this one is the best by this amount, and so I want you to make more responses like this one. This is faster than the critic model, and it's also simpler to scale for these really large models such as LLMs that are going to need to train for a really long time and are already super costly to train. Go to the next. Formally, this is what GRPO is. For each question queue, to each prompt in the data set, we are sampling a group of outputs from based on the old policy and maximizing this big long equation. We've got a couple hyperparameters in there. AI, as you'll see there at the bottom, that's the advantage. That's the how good are you by how much? How much better are you than everybody else that was generated in this batch? In English, this is the process of generating a set of responses, calculating the rewards for each response based on a much simpler, usually rule-based policy, comparing the results within that batch, and then updating the policy to favor the better responses, but doing so in a way that encourages and ensures stability in the model without it just kind of spiraling off into its own thing. And then, of course, we regularize the updates to prevent, again, drifting away from those ideals. The other thing you're going to see a lot, especially in the figures and in the tables, is this AIM 2024 benchmark. This is the American Invitational Mathematics Examination for this past year. It includes a number of math problems, specifically word problems. So like we've got an example here. This It includes a bunch of word problems. This isn't too tricky of an algebra problem on its own if you break it down. However, the fact that we're introducing characters and it's a decently long word problem means that it's testing a comprehension of these ideals instead of strict mathematical competence, although of course it does test how well you can actually solve the math problem. There's two metrics. The first one is pass at 1. This is based on the pass at K metric that was published a few years ago. And pass at 1 is the average correctness of K responses. So again, if we ask the model this question K times, usually between 4 and 64, what is the average correctness of those responses? With math, it's kind of simpler to say, okay, what percentage of them are simply correct? But when you take into account like weird formatting stuff, this can get a little more complicated. I capitalized it there. We also have cons at 64, consensus at 64. This is simply based on majority voting, again, from a few years ago. This is the correctness of the majority vote of 64 responses. So if I ask the question 64 times and get 64 answers back, what's the one answer that the most people voted for? And then is that one answer correct? So you'll see pass at 1 and cons at 64 in quite a few tables. But now let's talk about DeepSeek-R1 0. I'm going to refer to it as R1 0 because it is a mouthful. So the reason I just went over all of that is because R1 0 uses GRPO reward modeling. And as I mentioned, it does use a rule-based reward system for calculating which responses are better than the other ones in its batch. The goal of using this rule-based reward system and GRPO instead of more traditional reinforcement learning, in addition to some of the cost-saving and time-saving benefits I talked about earlier, are to prevent reward hacking and shortcutting the reasoning process. This also allows the researchers to simplify the training process and the training pipeline. But it also allows the model to reason without a lot of restraint put on of how it's doing it, in the hopes that we see some interesting emergent properties down the line. For this rule-based reward system, at least initially, we're focused on two things. Accuracy rewards. Is the response correct? This does require that the model follow some kind of format, such as put your final answer between 2 brackets or use this line at the end. But in general, we're simply looking for the accuracy and whether we can detect it. And formatting rewards. Did the model follow this given format, specifically this format? So you'll notice there down at the end that there's a specific format that is provided. The reasoning process and answer are enclosed within these think tags and these answer tags respectively. So ideally, all of your reasoning, all of this chain of thought, complicated reasoning is happening within the think tags. And then afterwards, there are answer tags, and inside of those answer tags is in fact the final answer. Now, they don't specify anything about the prompt. The prompts change with regards to the specific reasoning question during training, but every one of those prompts begins with this instruction to follow this format. Now, one of the things that they looked at was how was the model doing throughout its training. So we see steps along the x-axis for the reinforcement learning steps, and we're looking at that AIM 24 accuracy that I showed you earlier. The blue line is the pass at 1 metric. Ideally, it would like to get up to the green line, which is where OpenAI's 01, this is the 0912 model, is at. And the red line is the cons at 16. Apparently it's not 64 in this case. This is cons at 16, which would like to hit the pink line, which it does, and that's OpenAI's current record there. And we can see that while it's not quite matching OpenAI in terms of pass at 1, it's between the responses, the average accuracy may not be there. When you consider majority voting, it's up there. It's up there with OpenAI. More numerically speaking, we can see that the R10 model isn't usually better than OpenAI. I mean, it is, like I said, in the cons 64 section of AIM 2024, and on this other math data set, Math 500. It's a little bit better, a couple of percentage points, but most of the time, OpenAI's 0912 model is still doing better, especially on data sets like Live Code Bench and Code Forces. While the R10 model did relatively well on like mathematical questions, once it started getting into code, it became a little less impressive. It couldn't even beat the 01 mini model. However, the researchers did notice something that they refer to as self-evolution of the model. Again, steps in the RL process are along the x-axis, and the y-axis is the average length of the response. That think section of the response is what's growing. We're going from tens, a couple hundred tokens there, to thousands to tens of thousands of tokens during that think process. And while I'm not going to claim that more tokens equals more reasoning, it is interesting to see the growth of tokens, the growth of the amount of tokens over that time period. And the researchers found that in a lot of these cases, the length of tokens was increasing, not simply because the model was attempting to throw more words at the page, at the output, which it may have at the beginning, but because it was seeing evidence of reflection on its previous steps. They were seeing exploration of alternative approaches of, I tried this, have I tried that? Let's try that for a little while. And that's why we're seeing this growth of tokens. In terms of reflection on its previous moment, the researchers found this particular example that was produced. They call this the aha moment. Presumably because that's what the model called it. They said that's an aha moment I can flag there. This is a simple question of if A is greater than 1, and we have a sum of real solutions, yada, yada, yada. There's a response. It's a pretty lengthy response. It's a lot of algebra. But then about halfway through the response, it even says, wait, that's an aha moment I can flag there. Let's reevaluate this step by step, which, whether or not it's, I'm not going to claim it's gained sentience. They have not claimed it's gained sentience, but they do point out that it is rethinking in a very anthropomorphic tone. And because the prompt we gave it was so specific of just think and then give us the answer, it is interesting that it has picked up this anthropomorphic tone. And this is the power and beauty of reinforcement learning. Of course, this is a huge advantage. This is very unexpected from people who never thought to use reinforcement learning for this type of task before. And it did do reasonably well. These are pretty powerful reasoning behaviors from a model that only was trained using reinforcement learning after initial pre-training. However, some of the drawbacks that they didn't show these beautiful examples of in the figures were poor readability, especially in the math questions. Sometimes it would just kind of throw numbers at the page, which seemed to help it, but I don't think any of us could decipher what it was doing. And then language mixing. Because DeepSeek v3 base was also trained on Chinese and code as well as on English, the model had a habit of, in the think process, switching between all of them, which, if it was annoying for the authors who spoke both of those languages and knew the code languages that it was based on, if that was annoying to them, as somebody who does not know every coding language and does not speak Chinese, this would take the readability down to 0 for me. Additionally, there was some poor performance on some non-reasoning creative tasks if you tried to have it role play as somebody else, or if you wanted it to create a prompt for an original story. It was really bad at that. So, how do we improve on R10? Well, we go to R1. So, can we get better results from R10 by doing just a little bit of fine-tuning? Not a ton, not as much as you would for something like a traditional OpenAI model or even like a llama model, but just a little bit of fine-tuning. And then can we train it to produce a clearer and more coherent chain of thoughts without sacrificing this reasoning capabilities that reinforcement learning has instilled within it? So now we've got a full pipeline of training. We're still starting with DeepSeek v3 base. We're not starting with the R10. That was just like a different experiment, a different test. So we're starting again with the v3 base. Then we're doing a little bit of cold start fine-tuning. So again, a little bit of fine-tuning just to start off to try to get us over some of those initial local minimas. Then we're doing more of this reasoning-oriented reinforcement learning to try to, once again, build up those emergent reasoning properties. Then we're going to do another more significant round of supervised fine-tuning to try to expand the system capabilities a little bit. And then we're going to do a second reinforcement learning stage, mostly to help with keeping the model harmless, but keeping it helpful. And at the end of all of this, we end up with DeepSeek-R1. So let's go through this a little bit more specifically. Starting with the cold start fine-tuning. Again, this is meant to prevent the early, very unstable phase of reinforcement learning that probably contributes to why most people don't try this. This is also meant to improve readability. If we can negate that language mixing at the very beginning, hopefully it doesn't crop up again later in the process. Additionally, this would ideally lead to better performance in some of the benchmarks. But in order to do this fine-tuning, we need data to do this fine-tuning. So we're collecting some long chain of thought data from the R10 model. Sometimes they did this by few-shot prompting the model with examples of chains of thought that they would like to see. Sometimes they just directly prompted the model, said, hey, use reflection and verification to give me these long chain of thought models, and didn't provide it with any examples. Then it gathered all of these outputs in a readable format. Again, those tags of think and answer should be there. So we want to make sure that those are there and that any spacing and whatnot is readable both to us and to the model. And also there was some post-processing by human annotators to, once again, pull out things like language mixing and, jumps and faulty reasoning and whatnot. So ideally, we end up with just a bit of data. And so after fine-tuning on that, we use that reasoning-oriented reinforcement learning that we did with R10. Additionally, we introduced this new reward into the reward model. in addition to accuracy and how closely it follows the format, we are now looking at language consistency. Because unfortunately, just fine-tuning it did not, in fact, completely kill the language mixing. And this was enough of an issue that they incorporated this new third rule in the rule-based reward system to be how consistent are you on the language. They did do an ablation experiment. This does decrease performance. They did not say by how much, but it does decrease the performance. However, they said that they were willing to take this performance loss because of how much it helps with readability. And if the main goal of these models is to be used by humans, they need to be readable by humans. We then do, like I said, another round of supervised fine-tuning. This one's a little bit bigger of a round. This time specifically, we are looking at enhancing the model's capabilities in a non-reasoning, very general purpose tasks. So in order to collect data for this, we're mostly looking at reasoning data because we don't want to lose the reasoning process. If we just re-fine-tune on non-reasoning data, we probably lose it. But we want to keep the reasoning. So we pull 600,000 samples from the last checkpoint that we just trained of DeepSeek-R1. And what's worth noting is that now we're not just pulling data that could be evaluated using the rules-based reward system. Now we're looking at things that don't have just a strict right or wrong answer, yes or no. Now we're looking at longer, more complicated problems where partial credit, so you may say, is a possibility. And we're using other large language models as judges here to help with that reward system, as well as some other RL techniques I'll talk about later. But we do want to pull in some non-reasoning data. So we pull in 200,000 chain of thought examples from the base model again, because we've trained the base model to be a reasoning model now, so we have to go back to the base model to get some non-reasoning stuff. Pulling it from its supervised fine-tuning data set, and these are things like writing, how skilled are you at writing in various styles? Factuality, a bunch of common sense, but also specialized data question answering. Self-cognition, how aware of you and of your limitations. Questions about that. A little bit of translation. If we're going to have a model that can switch between Chinese and English, it should probably be able to translate between Chinese and English pretty well. If not, we might have an issue. We then fine-tune on this data set for 2 epochs to try and, again, enhance these the capabilities in non-reasoning tasks. We then go into our second reinforcement learning stage. As I mentioned, this is specifically to improve helpfulness and harmlessness through a combination of the GRPO reward model that we've talked about previously, but also some more traditional human preference reward models. These are especially important on those non-reasoning tasks that we can't evaluate by simply going, are you accurate? That's not how that works, unfortunately. Something else that's worth noting is when we're evaluating helpfulness, the authors very specifically chose to focus on just the final summary or final answer that was produced by the model. So they did not consider the reasoning process or what we might consider a chain of thought explanation to be at all relevant to how helpful the model was. They only looked at the final answer or the final summary. However, when it came to harmlessness, we are considering the entire chain of thought response. Even if it doesn't show up in the final answer, something harmful could be said in the middle of there that could, that could be harmful. So now we want to run a bunch of experiments. They ran a bunch of experiments, a lot of benchmarks. The first set is a set of standard benchmarks. These are ones that have right or wrong answers. We're seeing a lot of the English benchmarks, so the MMLU sets, if eval, frames, simple QA, C simple QA, some coding ones like Live Code Bench, Code Forces, math ones like AIM 2024 again. But also they're trying to use a couple of open-ended benchmarks where they could use an external language model like that has evaluated many other models before it to see how they do on those benchmarks. These were Alpaca Eval 2.0 and Arena Hard. Something that should be noted, however, is that in terms of prompting, they went with 0 shot whenever possible, including when that was not standard for the benchmark. For several of these benchmarks where the standard prompt had several examples in it, they actually went in and modified it to be 0 shot. They found that having few shot examples in the prompt actually made the model perform worse than if it was 0 shot. Here are all the numbers. There's a lot of numbers. I'm going to talk about the important ones. I mean, they're all important in their own right, but some of them are more interesting than others. So the first thing we want to look at is the English data sets. This is most of them. On the far right, we have the DeepSeek-R1 model. There's a couple of other models in there. The most exciting ones are, as I said, the R1 model on the far right-hand side, and then next to it are the OpenAI models. Something that they did mention is apparently it is difficult to get a hold of access to OpenAI's latest models in mainland China. And so the reason they don't have a lot of OpenAI numbers in here is because they had to go off of what was reported from OpenAI officially. So they simply could not run more tests and had to rely on OpenAI's numbers. But one thing that they noticed, the researchers noticed right away, is that if you were to compare these R1 models to the DeepSeek V3 models, that base model that we started with, we're seeing a pretty big improvement. You know, sometimes only by a couple of percentage points. But other times we're seeing 9 percentage points, 10 percentage points. You know, the GPQA Diamond data set, you know, we're seeing over 10 percentage points. So this process of fine-tune reinforcement learning is producing pretty significant results compared to the base model. We're not quite up to OpenAI's level on a lot of these. Some of them were very close, like MMLU 91.8 versus 90.8. That is clearly a difference, but it's not as significant as it might otherwise be. The other ones they specifically called out were the coding and the math data sets. Now, in the math data sets, you'll notice that while not always by a lot, and again, we are missing data for the CNMO 2024 dataset from OpenAI, DeepSeek-R1 performed better than OpenAI in those data sets. Not always then in the code data sets. OpenAI was able to eke out a few data set wins there. But we're still seeing very significant improvement over the base model, and we're seeing competitive results with the 01-12-17 model, even if this model isn't beating it every single time. I do want to talk about the distillation because that was something that was brought up at the beginning and has, honestly, some of the more exciting potential in this paper. So the idea is to fine-tune small open source models, namely Qwen and Llama models, on those 800,000 samples we previously gathered, those 600 reasoning samples and the 600,000 reasoning samples and the 200,000 non-reasoning samples. Since we pulled those from a checkpoint of R1 in the middle of its training, we are considering this distilling from the R1 model. So we start out with, I believe that's 5 Qwen models and 2 Llama models. Now, admittedly, we are starting with some pretty big models. I mean, 1.5 billion wouldn't be considered huge, but the Llama 3.370B is a pretty hefty model all on its own. But what the authors wanted to try was only using the supervised fine-tuning. any benefits from the reinforcement learning had to have come from the samples that were pulled from the R1 checkpoint. These models were not fine-tuned were not reinforcement learned at all. They were only fine-tuned. They also did a number of benchmarks to experiment with this as well. However, significantly fewer than they did with the R1, probably because they had now 5 distilled models to get through and test on everything. But as usual, we have the AIM 2024 benchmark, as well as some coding ones like Codeforces and Live Code Bench. Once again, lots of numbers, very impressive numbers, we think. Pretty impressive for what they are.
Did the meeting end?
Not sure. I also don't hear anything.
Yeah, none of us do. John, if you're there, we've lost it. We've lost audio.
Now we're back.
Okay. These are the important numbers in the table. So of the distilled models, unsurprisingly, the distilled model based on the biggest base model, Llama 7db, performed the best most of the time of the distilled models. However, the largest Quen model, the 32 billion parameter model, also did decently well in a couple of these benchmarks. Additionally, in terms of the non-distilled models, namely looking at the GPT series, OpenAI's O1 series, and Claude, and this QWQ model, we can see that the O1 Mini is winning most of the time in terms of the non-distilled models. However, with the exception of Codeforces all the way on the right, for every other benchmark, one of the distilled models performed better than the best non-distilled models. Again, usually it's beating the O1 Mini as the best model. And even when the O1 Mini wasn't the best model, it was still beaten by one of the distilled models. I have to assume that the reason they're using the O1 Mini here for these experiments as opposed to the O1 1217 model is because, again, they didn't have access to the O1 and so could not run all the tests they wanted, whereas they did have access to O1 Mini and could run more experiments with it. So it's a little bit unclear how these results would stack up with the O1 1217, the actual most powerful OpenAI model right now. But at least in terms of the O1 Mini, these distilled models are doing fairly well. Again, with the exception of code forces, where the O1 Mini has a distinct advantage, and in fact, some of the distilled models do pretty poorly. The 1.5 billion not even cracking 1,000 points, which is might be a bit disappointing. I now want to go into some of the discussion around the results, including things like limitations, future work, all that good stuff. So a lot of what I just talked about with the distillation models was pure distillation fine-tuning. There was no reinforcement learning there. But what if we did it in anyway? What if we used reinforcement learning anyway? So if we want to get small models, if we don't want to be working with these giant models that are taking all of these energy and all of these resources, and we just want a small model, should we be using distillation? Get it? Is that truly the best way? Or since we just saw that using this long reinforcement learning process did so well on the base model, yes, DeepSeek v3 base is a very large model, but what if it works well on smaller models too? Maybe it's an option. It's not. Unfortunately, for anybody who was hoping to train these smaller models using really long reinforcement learning techniques to come up with the best model of its size, in every single benchmark that they tested it on for this experiment, the model that was distilled from the R1 model was better than the one that was trained using long reinforcement learning. That would be the middle one was trained using RL, and the bottom one was that model that was created from distillation. And it beat out the other one pretty significantly. Even in some cases, this QWQ model, which was not specifically trained in any way to do reasoning tasks particularly well, it was trained as a very general purpose model, it did better than the reinforcement learning model that was, a couple of times. So maybe we don't use reinforcement learning on these smaller models. Maybe we just use it on the larger models and then distill those models into smaller models. If you want that seems to be the better way to go if you want a really good small model. There were also a couple of things that the authors tried that didn't work, namely process reward modeling, because it was really difficult for them to define these individual steps to push the model towards. Usually you would say, okay, maybe we can't push you to the final answer right away, but we can push you in the right direction. You're performing the right steps. You've got the right idea. However, when you're trying to train it in a concept as broad as all of reasoning, in the English language, in the Chinese language, on math problems and on coding problems, how do you define a step of reasoning? They couldn't. Anytime they tried to define it, it didn't go super well. So this PRM technique didn't seem to work. They also tried Monte Carlo tree search because that has proven to work very well in certain settings of reasoning, especially chess and AlphaGo. However, those are both games with a very defined search space of what you can do next at any given step. Language doesn't exactly work like that. They did try to constrain the search space and said, okay, well, one step is, I think it was like a couple thousand tokens, and that's a step. So let's do tree search on every combination of up to 3,000 tokens and see where that gets us. But in addition to taking forever, it also requires that pre-trained value model to give us reward values. That was the whole reason we're using GRPO instead in the first place. So while it's an interesting idea, and I would be curious to see if it could be used for some very specific types of reasoning, for this very general use case of reasoning, it didn't work super well. There's also a lot of future work to be done. Future work, what some of the limitations of their model are. as previously mentioned, using long chain of thought on non-reasoning tasks, while theoretically they've done it, it doesn't work super well, especially when you're doing things like creative writing, role playing, that kind of stuff. Actual, knowledge, storing and remembering. Long reasoning chains aren't going to help you if you don't remember what the capital of France is. Unless you've got a map in front of you, you can't reason your way into that. Additionally, they want to improve, and by improve we mean discourage this language mixing. Instead, they'd like to be able to specifically tell the model, hey, I want you to give me the reasoning and the chain of thought and answer in English or Chinese or in JSON. It's really bad at JSON. I don't know why they brought up the JSON specifically, but it was not good at producing JSON answers. Additionally, as I previously mentioned, it is very sensitive to prompts. It does not like few-shot prompts. It prefers to do its own thing. It does not want you to give it any examples of what it wants, which, on the one hand, is nice for those of us who don't like making few-shot prompts. On the other hand, sometimes the easiest way to explain what you want to see is just to give an example, and the fact that that is causing a degradation of performance is also very frustrating. There's also, however, these ideas, they call this large-scale, long reinforcement learning, worked really well for creating a language model that performs really well on reasoning-based benchmarks. What other engineering tasks are there, especially in the machine learning world, that could also benefit from this large-scale reinforcement learning that nobody's tried yet because it either, because no one thought it could be done, or because the policy model was too big or too costly, but maybe now it could be done. Thank you all for being here. I think we've got about 20 minutes for questions.
Thanks for Boy.
Here's what papers I cited.
So it's interesting about the JSON. You said, I don't know why they wanted JSON, but that's kind of a go-to for things like GPT-4 for getting structure. Yeah, like for example, just simple example in ChatBS Next Gen, having LLM generated structured output, given an example of the structure that you want, fill in these templates is kind of a often used thing. Well, with Llama as well. But so I could see where if it's not following directions, that's a bad thing.
Yeah, that would explain it then.
Yeah. The pipeline for I was it the distillation, the real R1, not R1 early, that one pipeline.
Yep, I know what slide you're talking about. This one?
Yes. Was there any sort of breakdown in terms of the time invested in each of these steps? Like,
unfortunately, no. The only kind of guess I have is that cold start fine tuning probably took a lot longer relative to how much space it took in the paper, because they mentioned that they used human annotators to ensure quality of that data. No details on what instructions those annotators were given or what specifically they were looking for. But that took a while, at least in terms of the human time and human cost. But no, they didn't break down any sort of computational cost or whatnot involved with each of the steps, or overall.
well, this coupled with the assets involved in doing each of these steps would kind of be the crown jewels in terms of describing what exactly was going on.
Mm-hmm.
More questions, got to be tons of questions.
For me, the most fascinating thing, I don't, it's not really a question. The language mixing is the most fascinating thing.
Mm-hmm.
And I suppose this could mean that Chinese and English and some other, whatever, JSON or whatever, they somehow cover the whole semantic space. So if you want to have precisely express some meaning, potentially you can do this in one language. You have to, because they're not exactly covering the same space. So in order to say everything in English, you have to sacrifice some semantic accuracy because you're lacking certain concepts or words to express that. This is why the performance goes down, right? So
The best way to say it is to mix everything.
to spill out this thing with a mix of code, Chinese and English, and this is the wisdom, right? And now if you want to translate the whole thing into English, then do this. Right? But I am the oracle, and I spill out all this stuff, and this all is good. And now you can translate it into whatever you want, right? Yeah. I think it's fascinating.
It did seem like they put a lot of effort in trying to stop it from doing that. I mean, that was part of the reason for the cold start fine tuning, for the supervised fine tuning stage, for that second RL stage with the helpfulness. And they still never quite got it to stop doing that. So yeah, it does seem like it's pretty deeply baked in.
Maybe they should.
Maybe it is like
they shouldn't be doing that. They should have a translator up front, translate it into whatever audience needs that.
You're saying that they're holding it back from its true identity. So I had a question. So we've been hearing a lot about things like it won't answer questions about Tiananmen Square and stuff like that.
Yes.
And it sounded to me, I think that's introduced at the doing no harm stage. I know you've got probably a better slide that this is, I can't remember exactly what you got into, where, yes, the helpfulness and harmlessness.
Mm-hmm.
To me, that's kind of a euphemism. It could be interpreted as a euphemism for making sure it doesn't answer questions in a way that that are not politically correct for a particular politics.
So
Is that where it would happen? Or?
I mean, it very well may. If I had to pick a stage where it would happen, it would almost certainly be this one. Just like you said, because of its emphasis on helpful and harmless. However, I've also seen some people run some experiments on the DeepSeek models that imply that if you ask the questions a certain way, like if you're asking it to use like leet speak, then it will talk about those events, which seems to imply that rather than the model refusing to produce it, it's a layer on top of the model filtering it out and saying, actually, you produced this, you're not allowed to say that, produce something else.
Okay.
Now, that's my interpretation based on a couple of blog posts. They did not mention that at all in this paper, and I couldn't find any sort of information on like the data that they train on. Like they talked about, oh, we've got these 800,000 training samples, and this is what we're distilling the models on. And I can't find those 8,000 training samples. So maybe it is here. I don't know.
Yeah. So again, the same question I asked.
Sure.
The paper, do they mention like any hypothesis they have to why zero shot does not work as well as few shot?
So while they didn't provide any like empirical reasoning, their assumption, I'm going to call it that, is that the few shot models are limiting it, they're forcing it, or at least encouraging it to follow a pattern, and that pattern is not the best way for it to solve the problem. And so because it's trying to fit into this mold, it's not actually doing its best to solve the problem. And so, removing the few shot examples, removing the mold is allowing it to perform better. Which,
Can you all hear me?
Yes,
Yes.
you can, Jim.
All right. My question is about the distillation. Can you go to that slide? The one
I can.
where I tried to see whether it would work.
Abraham, sorry.
Yeah. I think this is a later slide, the one where they were comparing small model trained with RL from scratch to distillation. Yeah, here. So are they comparing here in DeepSeek-R1 distill Quen 32B, is that distilled from the final R1 or from R1 0?
So that's distilled from the final R1. The R1, so R1 distill Quen is the one that is distilled from the final R1. R1 0 Quen is Quen trained using the same reinforcement learning as R1 0.
Okay, so that's what I kind of thought, and I was wondering if that's a fair comparison, because when you distill the final R1 down to distill Quen 32B, then that's also including distillation of all of the other post-training that it had, including the preference tuning. Whereas, could it be that it's really that's causing this dramatic increase in the metrics here, rather than inefficient or ineffectiveness of the reinforcement process for small models?
It's certainly possible. I would be a little bit surprised if it was just that, simply because of the scale of the discrepancy. You know, we're seeing a lot of the times 10, sometimes 20 percentage points difference. And I would think that would mean there's something deeper going on than just, oh, this one didn't have any fine tuning. But it is certainly possible.
Okay. Yeah. Did they discuss this at all in the paper? If you remember?
No.
I didn't. Okay.
No, they did not.
Okay. All right. Thanks.
Thank you. So,
I have a question. So basically, it is about the reasoning capability. When I understand, like, there is two separate sections probably related to this thing, like that GRPO, the group policy optimization thing, and having thinking token in the prompt. So my question is, have they mentioned why it is better in reasoning? Because ultimately GRPO is like grouped version of RLHF, right?
yes.
So why RLHF couldn't be able to do reasoning, but here they can?
So are you asking why specifically GRPO was used as opposed
Like
to
basically,
reinforcement learning technique?
what component specifically causes to make this better in reasoning? Have they mentioned?
I don't think that the paper was specifically arguing that GRPO is the best reinforcement learning technique to use. They certainly said that it was better than, come on, nope. I'll get to the slide eventually. They certainly said it was better than these two, than process reward modeling and Monte Carlo tree search. But there's more than just 3 types out there. I think the point that they were trying to make with the GRPO is that the reason nobody else has tried to just use reinforcement learning to train an entire model is because of how expensive and difficult it is to do. And GRPO enables us to try and do this long reinforcement learning. So rather than GRPO being a silver bullet for reasoning, it's a more effective way to do this technique at scale. So it's fixing the scalability problem of reinforcement.
Oh yeah. So, but it's still like my curiosity is that like ultimately this is a next word prediction problem, and it fills out the thinking.
Yes.
And in evaluation process or the model optimization, we optimized whether or not the final answer is correct or not the thinking pattern, right?
So correct. We were looking at whether or not the answer is correct, and we're looking at whether or not it did follow the format. So as long as it put something in the think portion, and that something, wasn't nothing, and that thing exists, and the correct answer was within the answer brackets, you're absolutely correct. There was nothing that looked at the thinking process to say whether that was correct or not. We just said, it's there. Let's move on.
That's the weirdness I'm having. Like, why that thinking part got better?
Yeah, and I I don't know either. This is something that I find particularly fascinating about. Where is it? No, it is right here.
Right.
About these results in particular, this aha moment, this anthropomorphic tone in this thinking section. We're not trying to train it to do this, but this emerged as a process of the training anyway. And I don't think this paper is trying to explain that emergent property. I think it's more talking about the fact that it showed up, it's there. So it would be very interesting to look into. I don't even know if they've looked into it at this point, given how new this is.
And it does this aha moment in English or in Chinese?
I'm taking them at their word that this was a direct copy of something that was written by the model, which in this case means that that line was written in English. Now, there's a couple of dots surrounding there. I don't know what language those are in. But it does seem like this was in English.
Okay.
So are they indicating, so they were going down one solution path, a viable solution path.
Mm-hmm.
And the whole point of this aha thing is, well, there's another solution path, an alternate solution path. Is it necessary to think it's better or just an alternate, found an alternate as well?
I think just that it found an alternate. There was evidence of it searching down, doing something almost similar to tree search, tree of thought, not quite as formalized, but something similar. But then it did the reevaluation of those alternating branches using the phrase, "That's an aha moment."
Well, I guess, yeah, because I'm wondering if we're overplaying this. Wait, there's another, they could have just alternate solution.
Yeah. Yeah.
I mean, we all get excited when we're.
I have another thing, like probably this is a quack I got. So, and basically it is surrounding the pass at one valuation matrix. So my confusion here is like, if this pass at one works like we give expected answer and generated answer and check whether those are similar, then how would it be the model would get higher marks when the generated answer in mixed language than in English? Because like it obviously should not be similar.
So I cannot guarantee this, but what it seems to be is that all of the reasoning benchmarks that they looked in had numeric answers. Oh. So the final answer should be a number, not a phrase. When they analyzed it where it was more open-ended, they had to use another large language model as a judge. So the language mixing was less a problem for calculating pass at 1 and cons at 64, because we're just looking at numbers and we're not considering the actual reasoning process behind it.
Okay, thank you.
This is sort of related to the resource allocation question I had before.
Sure.
Was there any reference, not necessarily in the paper, but a reference to some other sources about how they allocated all these people, how they managed all the people? But more than 100 co-authors claimed on the thing, but it's obvious as you went through particular later portions of the discussion, there's a huge amount of people executing a huge amount of tasks to construct just the infrastructure for this.
So they did divide the authors up a little bit, not necessarily by task or which portion they contributed to, but they did sort authors into core contributors, which are the ones I put on the title slide as the main authors. And I believe they called them associate contributors. And they also flagged everybody who had worked on the project, but had since left DeepSeek before the publishing of the paper. So it can be assumed that they did a little bit less than even the regular associate members. So they didn't say who did what, but we can at least pinpoint the ones who did the most. But I haven't seen anything specific about more precise allocation of work.
The kind of related note, like, have they given any information about training time and the like computation power?
So I know there have been some reports on the training time. They didn't discuss that in this paper. The goal of this paper seemed to be, hey, reinforcement learning leads to emergent reasoning properties, and GRPO enables that, not necessarily, hey, GRPO enables us to do that at this speed. I know there is data published on that, though, because a lot of people, have written blog posts about how much faster it was to train the R1 model than it would have been to train the 01, 12, 17 model. I didn't look into that. I know it's out there, though, for you to look into and for you to find the paper, and you can do the next paper discussion.
Oh, there we go. There we go. Ouch, ouch. Left it as exercise to the student.
I got another question.
Sure.
So typically when you train a language model, either in the, or well, if you think about post-training, fine-tuning, typically if you only have a single domain, such as math problems in the training set, it leads to some kind of overfitting. And here they managed to avoid that. And my understanding is that they didn't apply a loss on the question, and they didn't apply a loss on what came between the thinking tags. They only applied a loss on the answer, and that loss was also only provided by GRPO. It wasn't, your typical cross entropy. So they're essentially they're not adjusting the weights. They're not rewarding or penalizing anything that directly happened between the start of the sequence up until the answer phase. But it's still surprising to me that they could get away with this with just math and see a huge performance boost in all of those other domains, such as Arena Hard and whatever else they did. Did they talk about that generalization at all?
So, real quick, before I go into a little bit more into GRPO, I do want to note that it did take some generalizability loss. They didn't discuss it much, but it does seem like the base model did better on tasks like creative writing and role playing and whatnot. So while it didn't overcorrect so much for one specific benchmark, it did seem like there was some loss of generalizability into these non-reasoning domains. One thing I do want to bring up, though, because you mentioned it, is if you look on the very right-hand side of equation 1, you'll see this beta hyperparameter and then the KL divergence between the new policy that we're optimizing and the reference policy. And the reference policy is the base model. So again, I'm not an expert on reinforcement learning, but I would have to guess that part of the reason we didn't see a lot of drastic overfitting was because it is slightly punishing how different it gets from the base model.
Got it. Yeah, it's like anchored training, right? Anchored fine tuning.
Yes.
So I just want to make sure that I'm understanding correctly. The policy is how it's selecting. It's the factor that it's for selecting from the mixture of experts, or is this? So when it updates the policy each time, how does that actually go into? How does that affect the model's output, or how does the model actually use that policy to select the answer?
So, so the policy is how it generates the responses. Are you asking like how the reward function ties in, like the reward function ties into the process, or?
So sorry, I guess my understanding was it's a mixture of experts model, right? So it's generating multiple.
So the mixture of experts is part of the base model's architecture. It's kind of replacing the normal fast feed forward network at the end of a transformer block.
Okay.
So if you were to just ask DeepSeek v3 base something, it would only give you one answer. It's just that it has gone through multiple blocks where mixture of experts was used to select the best answer.
Oh, okay. I see. So it's not actually like still including that in the kind of final version. This is just how they, okay.
Yeah.
So I guess I'm struggling to understand how the reward function then ultimately affects. So if you're no longer including kind of that mixture of experts, then how does the policy, or how does updating the policy over time, how does that benefit like the end result?
Yeah, so we're not formally using mixture of experts. We are generating a set of outputs, just asking the same question over and over again. We're generating G outputs. The reward policy is what dictates that A1 at the AI at the bottom, because it's scoring based on accuracy and format and later on language consistency. So that's where we're getting these RI scores, because they're based on the responses or outputs, in this case, O1, O2, or whatever. Specifically, again, it's using the AI, trying to go through and minimize how different the new policy is compared to the old one, while still emphasizing the AI that did the best.
Okay.
So like if an AI did poorly, then we don't want to push the model in that direction. We want it to stay by the model, the old policy. Whereas if that AI is pretty big, we can afford to let the model go further away from where it just was. You know, it can take a little bit of a bigger step. Not too big of a step. That's what that clipping is for. It keeps it stable. But that's kind of how it's doing that. And then, of course, that policy is updating parameters and all that.
Okay, that makes sense. Yeah, that's I guess the question I was wondering about, like in terms of how does the policy apply? But it's related to the architecture of the model. Like whenever the policy is updated, that updates.
Oh, yeah. That pi theta is, that's the policy. That is the model. So updating that.
Oh, okay. So it's like literally a giant vector of. Okay, yeah, I see.
This paper, Xiao et al., also by the DeepSeek team, goes into a lot more depth. And there's also some very good blog posts out there attempting to explain this very long, complicated paper. So I don't promise to be an expert, but I did try to find this out.
Okay, great.
I know we're a little bit past 5. Does anybody else have any questions?
This has been really super. So let's. And thank you, Abraham, for providing Danielle's template.
Yes, thank you. I very much like your color scheme. So
yeah, and whoever's next up, you feel free to follow that same format. They've really set a great standard. Unless we got a better standard, I don't know. But,
I'm sure that was just a default PowerPoint template.
Well, it worked very well.
That's awesome.
Great.
So, and thank you to those who joined us remotely. We had several people remotely. And we're sorry that our audio cut out. I think we basically paused while we were getting the audio back, so you didn't miss anything. And I think in the ultimate video, I'll probably edit it out, although it was minutes. And one last thing, just a reminder: we are looking for other people this term. There are still some slots available. So, Tomek, if you've got any other people that you want to get in before the end of the term.
Yeah, anybody can do it. Yeah. Doesn't have to be, any paper you find interesting or your own work. You're welcome.
Well, that's right. Well, yes. Yeah. It doesn't have to be a paper discussion. That the regular part of a TWed is just talking about the topic of interest for everybody. But thank you very much. Have a great one.
Thank you, Danielle.